Hello, I'm Eduardo Aznar Gadea from the Electronic Materials and Devices Unit, and I'm going to present the work named Biocompatible Polymer Perovskite Nanocrystals Composites for Sensing Applications. In this work, we have developed a photoluminescent chemosensor based on a molecularly imprinted polymer nanocomposite of cesium lead bromide perovskite embedded in a polymer for the selective detection of explosive or explosive-like molecules. Moreover, we synthesize non-molecularly imprinted polymers to compare the results. A common strategy used for the fabrication of perovskite polymer nanocomposite films is to use ex situ methods. In this approach, nanoparticles are synthesized by wet chemistry as a colloidal solution and then is dispersed into a polymer solution, which is finally spin-coated to form a thin film, and the holes are formed when the bake process takes place. As a result, homogeneous and transparent thin films of the perovskite polycaprolactone nanocomposite were successfully generated. The spin coating speed was adjusted accordingly to prepare systematically 150 nanometers thick films. The presence of cesium lead bromide nanoparticles in the polycaprolactone matrix is confirmed by the PL spectrum peaked at 513 nanometers for both reference. The NIP sensor, that is the red curve in the graphic, and molecularly imprinted nanocomposite, which is the green curve in this graphic. The transduction mechanism of the cesium lead bromide nanocomposite is based on the high sensitivity of the PL of cesium lead bromide perovskite to local changes in their environment, for example when the analyte molecules are chemisorbed on their surface. Initially, we carried out the sensing studies of the analyte in vapor phase. The protocol followed for the analyte binding consists in exposing the nanocomposite sensors to vapors of the analyte of interest that we can see in the first figure. The following figures show the sensor response of NIP and MIP nanocomposites to 3-nitrotoluene. As can be observed, the PL intensity is very sensitive to the adsorption of nitro compounds at cesium lead bromide perovskites in such a way that the PL of the cesium lead bromide polycaprolactone film decreases by around 60% in the NIP sensor and 68% in the MIP sensor when exposed to the analyte for 5 minutes with. During this exposure time, any measurable shift of the PLP wavelength is observed. The real-time kinetic response of cesium lead bromide polycaprolactone films to 3-nitrotoluene as a function of exposure time can be better observed in this figure by using the normalized PL intensity as a response variable. As we can observe, the NIP sensor is faster than the MIP sensor, but the MIP sensor is more sensitive. Furthermore, both sensors are capable to sense this type of analytes because the PL intensity decays faster within the first 20–30 seconds, and after 50–60 seconds the sensor is saturated of analyte and the PL intensity decreases much more slowly. This figure shows the measured selectivity of the MIP and NIP films to different analytes for a fixed exposure time of 180 seconds. The PL intensity decreases significantly when exposed to nitro-containing molecules depending on the nitro compound. Therefore, our chip sensor approach exhibits very fast response, few seconds, and high selectivity for nitro-containing compounds. And finally, we can see in this image that the analyte adsorption on the sensor surface is a reversible process, For that reason, we can reuse the sensor, but the peel intensity of the MIP sensor can't be fully recovered because the template generates selective cavities and it's more difficult to remove the analyte from this side.